Good morning, day, afternoon to everybody, and welcome to the educational demo day of the QTEdu community. Today, we are really happy to have Qureka represented by Richard Kienhoefer. And Richard will tell us about their new, novel, very innovative educational kit to teach quantum computing, which is Qureka Box. I am looking forward, and the stage is yours, Richard.
Thanks, Oksana. Hi, everyone. Yeah, as Oksana said, my name is Ricky or Richard, and yeah, let me start sharing my screen, and we can I can tell you about the Qureka box. So the Qureka box is an educational kit that we've developed over the last year, 2 years. Um, that's going to teach quantum computing to either non-physics learners, elementary school students, undergraduates, anybody, all the way up to non-technical professionals. And this is using a methodology, our in-house developed methodology called ENSAR, which ensures that no abstract thinking is going to be required when learning quantum computing, which is a problem that I think we've all faced at some point. So students of all ages, from all the way from elementary school all the way to even PhD levels, they have these certain fears, frustrations that they developed through different classes, through the different teachers that they've had. And we can actually see these fears in certain statistics. So right now, on average, about 1/3 of freshman students actually don't make it into their sophomore year or their second year of college. And if we look at classes like accounting, physics, biology, chemistry, it's all kind of about that, about 1/3. But there's one subject that really stands out from everything else, and that's algebra. For some reason, algebra has about a 50% failure rate, which is a statistical outlier compared to the rest of the classes or the rest of the subjects, even compared to a subject like calculus. And these fears and frustrations come out, we believe, because of the abstract nature of mathematics and the kind of connection that students have with mathematics from elementary school. On top of this, there's a lot of frustrations. There's a lot of challenges that come with teaching subjects like these. Um, it's defining the science. What is the science when students first approach these kind of subjects? How are students going to define the subject for their students? Um, the teacher as well is not an expert in that science. They're not an expert in physics. They're not expert in mathematics, but they're a teacher, and their job is to just teach the subject based on the students understanding the science, what the best way to approach the students about this subject is, what the standards that the university or high school or elementary school or secondary school lay out for the teachers that they have to teach these kind of subjects. There's also never enough time to actually learn these subjects. So or at least to get into a deep enough level that every student is going to understand what that subject is. And then on top of that, it's very hard for certain math science subjects to actually happen in the classroom. How is like, as a teacher, a lot of you have to kind of think of how am I going to present this subject to the students. In physics, that can be lab experiments, that can be gravity tests. You can like throw a ball and measure how the distance, the speed. In chemistry, that can be mixing certain elements together to show the students, oh, this is actually what we're learning in theory is actually you can apply it. But in mathematics, a lot of the time it's very hard to remove that abstraction and to have the students really connect with mathematics. And then additionally to all this, teaching quantum computing just is another level above the fears and frustrations of the teachers and the students. The quantum computing relies on these mathematical formalisms that makes it very difficult to understand. The entire backbone of quantum computing is based on linear algebra, and if as a student you've never connected with linear algebra, you don't know exactly how to think about what algebra is telling you, it's very hard to connect with quantum computing. There's also just not enough trained educators in quantum computing. It's a brand new field, and to get new teachers, to get teachers interested, to upskill physics teachers is still a very big challenge that we have today. Additionally, there's not really a complete standardization of quantum computing teaching methodology, and wait, let me move this. And the kind of the lack of hands-on on learning in quantum computing makes it less engaging and makes it more challenging in the end. Currently, of course, we have online program exercises, we have the theory, we have different ways to approach it, but we can't really say that that's a full hands-on approach. And it makes connecting with it makes students' connection to this field significantly harder, or it's just more challenging. And so why is this important? So quantum computing is a massive emerging field, as I think most of us do know. There's there's a growing skills gap in the quantum technology and its workforce. Right now, even in the next 5 years, we're expecting the amount of workers to actually triple, and in the next 15 years, that's going to more than 10 or tenfold. I see something in the chat. Okay. And and the traditional education pathways that we have currently today are just not sufficient. We don't have enough students entering the field. And the demand for the field is ever increasing. The technology is getting more mature, but the students and the education that we have set up just isn't there yet. These Also, it's not just like physics degrees, it's technicians for the different quantum technologies, it's the engineers and the non-technical experts, or experts that understand what quantum is or quantum computing is, but they don't have to fully understand what like the math and the physics behind it. We're still missing a lot of those people. And that's why we developed okay, the Qureka box. And I was saying before, it is the educational or classroom tool that we've developed at Qureca based on this ENSAR methodology. And ENSAR is actually an acronym that we is actually like a reverse acronym, and it stands for experience, name, speak, apply, and repeat. And so by building this educational tool based on our ENSAR methodology, you see this? Does everyone see the slides? Or I think Oksana, do you still see the slides, by the way?
No, we can just see you, Ricky.
Okay, I'll reshare. But by building this educational tool based on this methodology, we're actually able to connect with students in a more physical way. So we're taking these abstract concepts and we're making them real. So how does this educational kit even work? So so each kit is up to 20 students per classroom, and we start with an initial and we end with a final assessment to just show the students or to show how much that they've improved over time. At the beginning, it's just each of the questions the students will not know. They don't have the background. They've never experienced these concepts before, and so we just encourage them to just fill in what they feel like. Um, then the final assessment, they will feel like, oh, I actually do know these subjects now. And based on our experiences from even elementary schools all the way to lawyers that we've taught, that they really engage with the subject and they experience and they feel their progress as they've learned. So each of these, so we've set up or we've divided our kit into 5 different modules. The first one is actually a like the way to think about quantum computing. So the world of the small, how what the kind of the mysteries of it is, and we approach this with different kind of materials. We also show them the history of quantum computing or of quantum mechanics first. So who are the important figures? What are the important dates? And we have them physically make this timeline for themselves. The second module is actually is teaching them what or showing them what superposition is and what wave particle duality is. And we do this in a couple of different we do this a couple different ways. But our main thing is actually with our qubit box. Oh, the blur is kind of but this box has a qubit in it, or what we like to call a qubit, and we show them how by spinning it, by naming these different colors, and which is very much part of the ENSAR methodology, how to actually think about what superposition is doing. And so we show them how to spin the ball. Oh, the thing's out. But show them how to spin the ball, how to close it, and then repeat what those names are, what is actually happening. And by going through this process or the ENSAR process, we're able to really drill in that kind of knowledge into their heads. The module 3 is actually then going from away from quantum computing or quantum mechanics in general and being more about the computing side. So what classical computing is, what quantum computing is, and then how to kind of arrange your these like cards into a way that makes sense. And one way we do that is actually through our compute cards, which are these kind of like little playing cards that we've developed. That you can play a few different ways. Which is the classical version and then the quantum version. And then we give them timers, we give them stopwatches, and we say, how long is this taking you? How long is this taking you? And what's the time difference between, oh, here's the parallel processing and here's the sequential computation processing. This is also where we teach them about entanglement and what the mystery of entanglement is and how we can think about that. The next module is the visualizing the quantum states, gates, and the circuits. And then we explore the block sphere and the linear algebra. And then module 5 is the culmination of all the concepts that we've taught them, and we show them how to actually code a quantum computer. So a little bit more in depth now. Sorry. So module 1 is the discovering the quantum world. So the students they're going to take the test. It's going to be just kind of simple. It's thinking of the concepts of quantum mechanics, but with simple objects. So with balls, if the classroom permits it, then we have a water bucket that we can show how the waves form, and then we define the history. And then the teachers. Oh, also as well, we have 2 different booklets. So one, how the teacher is the teaching booklet. So how the teacher should teach. I think I have it here. Oh, this is the student one. So we have a student booklet. The blur is kind of getting my way, but I think you get the point. Like a student booklet, and then oh, I don't have the teacher's booklet with me. And then we have a teacher's booklet that shows the teacher how to actually move through the content and which parts they should prioritize and which parts they should really focus on. The second one, as I said, is like kind of the immersion into the quantum phenomenon. It's the qubit box that we showed before, and we have the students build the qubit box themselves. So it's not like a built thing, but we give them the material, they put it together, and then they are the ones that name it. That they name it, they repeat it, they share it with their classmates, and that really connects them to what this phenomenon actually is, which is superposition, which a lot of students and a lot of teachers struggle to kind of tell someone like what it actually is. But if they experience it and they feel it with their hands, that's where the magic happens, kind of. Um, and then the teacher also has their own Qubit box. They go around explaining how to build it, and then they use that Qubit box and the supporting slides that we provide to teach and discuss the learning and tell them, okay, this is what this is. Um, we have a certain way of teaching them with like, no, that's not your name. Like you ask them what their name is, and then if they call the blue side, the blue state, a different name, then tell them like no, Daniel or something. And it's kind of fun. It's a little joke that we have between the students, and by doing that, they're able to actually be like, okay, I need to name this properly. And then that theme is also then played out throughout the entire rest of the Qubit of the Qureka box. Module 3 is the introduction to these compute cards that I was showing. So it's understanding how classical computing actually is performed, which which a lot of students like they have computers in their hands, they have computers at home and in on their desk, in their classroom and everything. But what actually is going on there, um, a lot of students don't understand that. So first we ask them to connect with that by playing this really fun game. Then we ask them, okay, let's switch it up. Let's show what quantum computing is actually performing. And then we time both of those and we say, hey, quantum computing actually in this kind of task is faster. And you can see that with this graph. And the teacher's role is to actually explain the rules and then to make sure that the students are following all those rules. The second section of the module 3 is the entanglement. So we have this entanglement experience where we have two different cards and envelopes, and the colors of those envelopes change as they're like right in front of their eyes. And that always blows. If we do it right, blows a lot of people's minds. Like, oh, like wow, like we're actually entangled. The colors are changing. Like that's the phenomena, or that's a concept that they can actually see in front of them. And then they're able to talk about that, like what's going on, how is it actually, how do you actually go through this, like what are we actually showing with this concept? And then we have a presentation that this teacher shows afterwards as well. The next module, module 4, is actually teaching them Dirac notation. Because we're not fully teaching them what linear algebra is, all the bits and pieces of linear algebra, we've actually developed a way to show what Dirac notation is by using objects. And so one way is you can kind of see at the bottom of the screen, we ask them to write a grocery list of different fruits. And we all agree on a fruit, we all agree on the number of fruits in our grocery list, and then we ask them to just erase the fruits. And now you just have a list of numbers, but because you've named it, you've said, okay, this is the cherry, this place is where the oranges are, these are where the apples are. If you just say that, if you just put the number, you put these two brackets on each other side, now it's Dirac notation. And we have these different cards. We have these different cards as well that they can physically move with their hands. They set up the notation. We ask them, show me what the zero state is, and they can move it around with their hand instead of writing it down. And that first kind of introduction into how to like the feeling of moving these parts around, the feeling of making the equation yourself is very empowering for the students. And the teacher's also there to explain how the bras and the cats are constructed, and to name it, to repeat the process, and to relate everything together. And here I wanted to show what the kind of the difference between the student handbook is and the booklet and the teacher's booklet are. So on the right side is the teacher's one, on the left side is the teacher's one, and the right side is the student's one. the teacher has an explanation of how these concepts are, how to actually perform these activities. So in this case, we can see that it's the linear algebra, the lists and vectors. So we have to explain to students what lists are, and what vectors are, and how can we go from this kind of grocery list a into bracket notation, into a list, and then what a vector is after that. There is a little bit of a logical leap here, but we found through experience that a lot of students, it clicks with them anyway. And then on the right side, we ask the students to fill in their supermarket items, fill in the numbers with them, and then now take that list and flip it on the side. So now you have, instead of a list going up and down, you have a list going side to side. The next section of module 4. So module 4 is probably our longest section in this, but is now you understand lists, you understand vectors. We get into matrices in this case, and then we ask them to physically move around these cards with their hands. And then the last section of this is then to take those the linear algebra that they just learned and put it onto a block sphere, which is a very important concept in quantum computing, and it teaches them what states really are. And if you want to see right here, we have the block sphere that they're able to move around with this little magnet on the side. By doing this, students are then going from this these cards, these equations into a physical object, and to connect these physical objects to how the students are thinking, or you connect these concepts to physical objects, it really helps how students are able to connect with the subject, how students are able to process what's going on. And because this is like a representation of the qubit itself, students are able to say, oh, okay, if I write this equation, if I have this kind of state, that means physically it's like this. And for students, that is a very powerful tool. And the last module, the students understand what quantum computing is what quantum is at this point. They understand the different kind of smaller subjects, or the different types of concepts. And now it's, okay, put this into practice, everyone. You understand the equations, you understand what it looks like. Now drag and drop with the Qiskit tool, or with the Qiskit composer, and you can see what is really going on. And yeah. So we ask them to create different exercises for themselves, to experiment. If they understand what's going on and they just want to play around with it, this is the chance that they get. It's here's what we taught you, now you can actually use it. Which, at least in my experience, that it's missing somewhat in classical education. So yeah, so those are the 5 modules, and we've had more than 10 workshops. We've organized more than 10 workshops at this point. We have both in English and Spanish. And at this point, we've trained more than 200 high schools and undergraduate students. So in the middle, you can kind of see me practicing with this group of researchers. I think on the right is actually PhD students who've taken this course. And even if you understand quantum computing, even if you this is my research subject, the way that it's presented is very enlightening even for PhD students. And yeah, this is just the last slide that I have for you. Now is the time to prepare your teams, your classrooms, your students for the year of quantum, because it's already started. And yeah, thank you for the invite, and hope to talk to you soon. Thanks.
Thanks a lot, Richard. This was a very deep and indeed extremely innovative tool. That's my personal perspective, because I've seen some tools around, and I would really like to have it in my hand one day.
Yeah, we can send a little block sphere to you.
Demo tool. So now I would like to invite all the participants to either raise the hand and speak up your questions or proposals, suggestions, comment, doubts, or excitement about the tool that we got presented by Richard. You can also write a chat, a question, and then I'll read it up for you. So we have comfortably half an hour. Let's warm up and start talking. And we already have a question from Francisca.
Hey,
Hi,
Francisco.
Richard. Nice to see you.
Yeah,
And
nice
thank
to
you
see you
very
again.
much for the presentation and introduction to the tool. It sounds really fascinating, and I agree with Oksana. I would like to have it in my hand. I have a question and a consideration.
Okay.
So I'm a bit afraid of oversimplification. If you say something like, okay, here's a block sphere, now you have the qubit in your hand. No, you have a visualization of the qubit state. And the risk that learners may think that inside the quantum computer, there are very, very small block spheres, for example.
Yeah, okay.
So I was thinking a bit, maybe you could think a bit about the wordings that you use and what you maybe suggest with the formulations you use in the materials and in the introduction and this kind of things. And especially for the entanglement, I didn't really understand how you do it with the colors, and so maybe you could explain a bit more detailed how it works.
Yeah,
So
I
that
can.
would be my question.
Yeah,
And
we have these like.
especially, yeah.
Oh yeah. Well, we have these
Yeah.
these little envelopes that we provide the students, and the way that we do it is just a small magic trick, but the way that it goes is a or the way that it actually works, we want to keep not a little secret, but like just so that I don't know, we want to keep it a little bit of a secret how that actually works, but it's a magic trick essentially.
And so what
But
do the teachers do, and what do the students do, and what do they see and experience?
so the teacher provides, let's see, what color are these? The teacher provides they get two students, they get little envelopes with these white cards, and they say, okay, put your envelope in the white card, and we're going to entangle both of you. And so we have them hold their cards. We wrap like a yarn around their hands, and then we perform this magic trick so that the colors that they have change. And then we unentangle them, and then we're like, okay, open your cards now. And when they open their cards, it's a different color. And of course, we are doing a small simplification for all these subjects. This is an introductory course. Of course, definitely where we are not we it was a little slip up right there, but we are not saying that this is a qubit like 100%. But we are simplifying a little bit so that we're able to physically put these things in their hands. Like, of course, a block sphere is not a qubit. Of course, like tying their hands together and changing the color is not real entanglement, but it's the ideas and putting it in their hands that is how we're able to connect them to connect them to the concept without going through like or removing the abstraction between them. Because like in math, if you just have some equation and you have some curve, I mean, a lot of students kind of like lose a little focus from there. Um, so yeah, it's just everything that we're putting together is so that the abstraction of those concepts is reduced.
Yeah.
Yeah, thanks for your
Okay,
question.
thank you very much. And yeah, especially for entanglement, for me personally, I think it's super important to clarify that all that what you do with some magic trick in classical objects is never entanglement, and that yeah, the magic is something different, but we can't see in our classical world.
Yeah.
But
Yes.
yeah. Okay. Thank you.
Thanks a lot, Francisca and
Yeah,
Richard,
thank you.
for this enlightening discussion. There was a quick question and answer in the chat. I was wondering if teachers are actually taught how to do magic tricks, because this is also a skill that is not coming immediately. And I see that Araceli is confirming this expectation of mine, that indeed this is the part of the training.
Yes.
That
So
is
of course it's not, we're not just giving you the booklet and saying, okay, just take this and you can learn, you can teach this subject. We do have a train the trainers approach, where we go to a classroom and we say, hey, or we get a teacher in and we say, this is the material, this is how you should teach it, and here's kind of like the kind of the outline of how to teach it or how to bring it into a classroom. And then we also, of course, teach them how the magic trick works.
okay. And do they then, in the end of the classroom, reveal that this magic trick to pupils or not?
No, that's the whole point. So like just to keep it as a magic trick is how is because entanglement is just magical in general. Like we don't
Really
really we
say
don't
that
have
magic
yeah, we keep it
without
in
saying
the
how.
magic.
Okay. Okay, Francisca is back.
Yeah, so
We have another hand up too.
so just to comment on this, I also agree something somehow that entanglement is magic, but I'm not sure if this is the message that we should spread to the world. Then it's again this, nobody understands it. It's magic, spooky. That's
The spooky magic at a
yeah.
distance.
No, it's well understood. It could be described completely, and it's just that we can't grasp it in our classical world. Yeah.
Diana, you had a question? Oh, sorry. The next question.
Yeah, hi. Yeah, and thank you very much, Richard, for this presentation. I completely understand Francisca's worries, because yeah, it's an ongoing discussion, right? Whether the like how to better present quantum in a way that it transmits the fact that as a scientist we already know everything about it, and it's just weird and spooky only because maybe we are not really able to transmit all the informations needed. But I would like to move a little bit from this discussion. I would rather ask you your thought process behind the development of this kind of tool, because you decided to show something very practical, something very physical that we can touch, we can see. But I don't. I would be curious to know if you also explored a little bit, like are there different ways to transmit this knowledge? Like why this showing this very material way of showing a block sphere rather than, I don't know, a virtual reality tool or something, let's say, completely different, because we could have many ways to visualize. We could give students many different ways to understand this kind of topics. But I'm just wondering whether the kind of thought process you had behind it, because it's something that I also struggle a lot with. So I want to understand other people, how they came up with this idea.
Yeah, so so one of the members of our team, he actually started teaching quantum computing, trying to get students kind of more. He wanted to teach quantum computing to students in Mexico, and he decided that it was he through trial and error he discovered that the way to get the way to kind of bring students in, trying to connect them with that kind of abstract concept, is by giving them like classroom material. And so what you kind of see in either like physics classes or just any other kind of in what's another good class? Like the physics experiments that you have, like you have two sensors and you try to measure the time between them and you perform the calculations for that, trying to get that kind of that that feeling into quantum computing. Because it it is hard to think of how can I show like a quantum concept like in a classroom without a computer. Like yeah, you can always show something on the computer, you can always code something, you can always plot a nice graph, but the connection between you and that computer is a lot more distant than if you did just the same thing on like the top of your desk. Um, and also like of course we've gone through we've gone to different groups, different like research groups, to different schools as well. Like this started as like a first year university kind of course, kind of crash course, and then it expanded into secondary and it expanded into like the professional level. And of course, just through trial and error that we've seen that these kind of materials do work, and it does connect people in a way that, like, of course we also develop online courses, and like people definitely very much enjoy that, but it's just having those things in your hands that really brings it all together. It makes everything make sense. It's like, okay, that's how that's supposed to work. Oh, that's how I can move around these equations. Because if you just have like a presentation on a screen and the teacher's like, these are the equations and you can move this around, it's impersonal that way.
Yeah,
I
thank
hope
you.
that I
Thank
hope
you.
that answers your question.
Yeah, yes, thank you for your answer. Not just because also on this topic, there's also discussion going on because, right, I mean, you can show the same topic on different ways, and every approach has its limitations. Like,
Exactly.
for example, this one, I'm speaking because also I developed some kind of exhibition using this kind of the same idea that you used, like having big tools that are just like an ideal representation of a quantum concept. And the issue there is always like oversimplification, right? I mean, I show you this, but actually this is nothing similar to the one to the thing I want to show you. Is just a way for you to create a mental framework somehow that I think is the correct one, but we never have the control over how this mental framework will develop in their mind. So
Yeah.
then maybe
Yeah,
some other
exactly.
people prefer to show, I don't know, a optical table with a simulator, and then you kind of perform the experiment, and then you have some data that you can analyze. And this is just a completely different approach, and everything has their limitations and their pros and cons. So just yeah, I'm always curious to know how people approach this, because I don't think there is a right way to do it. So
I mean,
I
this has definitely its limitation. It definitely has some limitations too, or a few limitations too. Of course, we can't go into the topics 100%. Be like, this is how linear algebra works, step by step by step. Of course, there's some simplifications. We found by teaching this, like, oh, there's like a small logical leap that we kind of make here. Um, but because the students themselves follow along very easily and very well, we're like, okay, I guess we'll make a little note of this. We'll explain that in the classroom. We made a little note in the teacher's manual after that point. That's like, okay, this is a logical leap. Just explain kind of this, and yeah, that seems to be it just seems to be working for as the introduction into this field. And then once they go from here into they start learning what the like Python and quantum computing, like even more in depth, then it's like, okay, these concepts that I learned before, they're ingrained now.
thank you for your answer.
Yeah, thanks for the question.
Mm. Yeah, waiting for the next questions. I would like to also ask one regarding the time that it requires for you to train teachers, and also the time that it requires to teachers to do through all the modules or each module. Like, how do they spend it usually? And then, but depends if there will be other questions coming or not. I'm curious if you could share with us one or two most recurrent misconceptions that students sometimes fall into, because as Diana was saying, there is no perfect method, and this is how you kind of measure unperfectness of the method. And I learned by doing research education that misconceptions are the best guidelines that we can actually use to
No,
improve.
that's true. Well, I think the time-wise, so it depends on the teacher and the and kind of the environment that you're teaching it in. We've been able to teach this in 3 to 5 days, like 3 days a lot of the time, um, like three full days. Other times our recommendation is like what is one module each week, so about 5 weeks. The entire length of the course is about 15 hours. So each module is about 3 hours, each. Um, but it can also be extended over a quarter, I would say. It's a little bit it's less than a semester. Um, it's not like a full semester length, but you could stretch it out to a quarter. The lowest amount of time is 15 hours for the entire concept. And then the misconceptions that students have.
While they are coming in your mind, the misconceptions. So how integrable is that with the schools that you tried? So is it usually included as a voluntarily vocational things that students do, or do teachers manage to fit that into the program recommendation? Like, okay, it's a kind of match of math and physics and computing science tack. We are happy, we cover it all a little bit. So how does the school manage to incorporate it?
Yeah, I mean, ideally, it definitely would be amazing if they were able to fit it in their educational like their course outline. But currently, it definitely is an extra it's an extra thing. So like either like an after school thing. I don't think we've had like a full like rollout for after school, but maybe we've done that in Mexico. Um, but yeah, currently it definitely is extra. And I'm still trying to think of the misconceptions. I mean, the things that take, I think, the most amount of time to teach, or like the most amount of explanation, be like, no, that's not correct. It's like this, is definitely the qubit box. So like trying to explain, okay, no, this is not blue. This is the blue state. And oh no, this is red blue state, and trying to just explain that in general to students, and just repeating that kind of concept is definitely probably is one of the harder parts, I would say. Um, Another one is probably is the fourth module where we explain the like the Dirac notation and trying to move things around, and they're like, oh, it goes like this, right? And then you have to explain, no, it's not like that. You have to move it around this way, because the people that we've taught before have never seen Dirac notation, or they don't know how that process moves around. So trying to explain, okay, no, like this is the state. This is like what this is your amplitude of the state. Like you can't just move it there. You have to explain this. Um, that's definitely, I mean, it's less of a misconception, more of a you've never seen this before. Here's actually how you do it. Um,
But then maybe if you think from the point of view of the evaluation, no? So you do the test in the beginning and in the end to show them what they have acquired. So generally in this very end, you could also see how many of them acquired and how many didn't. Typically, there is some kind of a success rate with acquiring the message. And so if we look from that side, do you have in your mind now what are the points of this assessments that you do that reveal the lowest success rate? Which I don't know what the number, if you want to share the numbers, would be fantastic. But even if you just say which points didn't reach the most, didn't hit all the people, for example.
So I know that the improvement rate is like their scores. So we recently actually updated the test itself, so we don't have like the full on we don't have the full on data for that. But our previous one, we saw their scores at least almost double. So it increased by like, I mean, there's a small amount of questions, so 93 to 95% increase. And so it's either that a lot of them either missed one question or they, it goes from 60%, 30, 40, 30, 40%, not 60, less than 50%, all the way to 95%. So either half of them miss one question or the other half get all of them correctly. But we've actually just changed the knowledge test as well, and so we don't have that much data from that. But we've added questions at the end that are more open-ended in a way that's like, oh, we didn't touch on this directly, but you should kind of understand these concepts now. Like, I can grab an example, or like yeah, so if the block sphere starts at state 0 and you apply an X gate, where is it supposed to go? And then we ask them, we have multiple choice, and then they answer. So like something like that we touch on, and we expect them to like move it around, be like, oh, if I have the X gate and I'm at 0, and then if I go here, we expect them to know that, but we don't like explicitly state that during the thing. I guess we do. But yeah, we just made it longer, the final version, than the initial one, so that it's like, okay, this is what you really learned. Like, these are the questions that are like open-ended. They're a little bit harder, and now we have like, now we can really see like, oh, students are actually learning pretty well, a better than we even thought. So.
That's impressive. When you mentioned 97 to 93 to 97, that's for science education research is actually a big hit. So congratulations.
I mean the
and then
it's like they have zero knowledge, and then it's like, okay, or like they have no idea what these concepts or these words mean, and it's like, oh, okay, these words mean this. Oh, okay, yeah, now I can link that together, and okay, these are the questions that like I understand that question now.
Yeah. So now I also imagine that you might expand the questionnaire in the end to see maybe they know even more than you ask currently.
Exactly.
Yeah, that will bring you more insights about how things are going. I see really nice exchange between Francisca and Araceli in the chat regarding. I just want to pick up on the message of Araceli. I wonder if the teachers know that, and this is related to the fact that it's important to state when simplification is presented that this is just a model and a simplification, no? And to my experience in different countries, the teacher education is approached in a different way. So I don't know how it is approached in Spain. In Germany, it's approached in a very intense way. It's a master degree in teaching at school, so that you need to go teach at school, and you need to learn 2 disciplines and the third discipline, which is a pedagogy, and it's a 5 years of learning. And I think in Germany, teachers might know this quite well, while in Italy, for example, there is no master degree on teaching. So you learn a matter physics or chemistry or math, and then you go teach in school. And recently there is something which is called like special credits, like 24 credits that you need to get, which is in pedagogy, anthropology, philosophy, things like this. And I have a bigger doubt that in Italy teachers have been communicated this well enough. So I think to this statement of Araceli, this wonder of Araceli is well, first of all, I share it as well. And I only hope that with your teaching tool, you are transmitting this important knowledge to the teachers as well.
Yeah, I mean that's at the beginning when we first introduce this, it is directly to the teachers. It's to tell them, yes, this is how you teach it. These are like the concepts that are either more of a model. Of course, the teachers also don't know what quantum computing is, but then afterwards they're like, okay, they understand it, and if they, I mean, of course, it's always an if the teachers like absorb all that. All the things that we say, but and then are able to replicate that with their own students. But I think they're going well so far, and yeah, but the point like of training the trainers is to show the teachers or the future teachers, hey, these are the concepts. You're going to go through it as a student, and then during that part, we're going to tell you that we're going to also say these are the models, like these are the important topics. This is how you should like present it to the students, and yeah.
We had a good tradition in the previous demo days that the offers were also described in terms of prices. I think that's very important also for our participants today to know what is the cost for the school to engage in such an innovative teaching, and also, well, from both points of view, to get trained and also to get the kit themselves for the classes.
Yeah, let me grab one thing here. Sorry. So the kit itself is, I don't want to quote the wrong price here.
I can put it in the chat if that helps.
Sure.
Yeah, but we don't sell the box alone anymore unless that we sell it to people that have already been trained. So first, it comes always with the training, because we realize that just the box, as Ricky was saying very well, is not going to be enough. So it comes train the trainers training, and then once the trainers would like to purchase the box separately, continuously, they can do it. But yeah, Ricky, if you have the prices, you
Yeah.
can say it. Thanks.
Of course, the training itself is 5,500 for and that includes the box at first, and then after that you don't need the training, and we ship the box, each one for 980.
980. Mm-hmm.
And of
you
course,
need
bulk
box.
prices as well. So if it's multiple boxes, each one will be a little bit different.
And once you use the box for 20 students, right? I got the Once you use the box and you want to teach again, you need another box, right?
No, so we offer not just the so once you have one box, then because there's certain materials that you reuse, and there's certain materials that you need to restock. So we offer like a refilling price. I don't know if do we have a price for the refilling yet? It's significantly less
No,
after that point.
it's just peanuts, really. It's like it goes like in a funnel. You know, like you start with the full trained trainers is around. Normally we say 7,000, but we have that discount for all of you, because this is kind of the beginning. That is and Ricky was saying, and it's the year of quantum. So we say 5,500 for the trainers or any training plus the box. Then you can have a reduced training that we have also done. So it could be instead of 15 hours or the 3 days, or let's say we can reduce the training and do it in 2 days or 3 days or 1.5. We have done kind of different
Depending on the time
models
scale.
depending on really the timings and everything, and then the price kind of goes accordingly. And then the box itself alone afterwards is 980, as Ricky said, and the refilling is just peanuts, because it depends what you really need. We just send it to you and it will probably cover just the shipping costs and a little bit more. So yeah, that's the model that we would like to have.
Okay, that's very nice. That's answers perfectly my question, and I think that now our participants have a complete picture of your offer, and I imagine whenever they have a question, they are free to contact you, and through the
Yeah.
contacts of
We
the
have a
web.
where was the either at info@Qureka.com or directly to Mira Aratheli. Yeah, there.
Okay.
And then you can find our emails and whatever social media platform.
Thank you so much, Richard and
Yeah.
Araceli, for being with us, for dedicating this time to explain the in-depth your work. I wish you good luck and good elaboration of the further teaching kids. So putting abstraction into objects is a hard job, and you are dedicating a lot of time to it. Thank you so much. We see the link, exactly, there is an email and the link in the chat, and we are looking forward so to the next training session in 1 month, so it will be 19th of February, and next time we will learn about another interactive teaching, although it will be about Schrödinger simulations, and it's called quantum movements. So this is just a teaser for the next time presentation. And with this, I would like to say goodbye to everybody, to wish you a nice continuation of the week, and take care of yourselves.
Right. Yeah. Thanks for having us. And thanks for everyone for coming.